This video is entitled Integration by Substitution. Now this is a very important concept to learn if you are moving on further in your calculus career, because if you don't learn this idea very well, it will make it difficult to learn more complicated integration ideas in the future. So with that being said, let's go ahead and get started. Now I'm actually starting with a derivative here to kind of show you how this works. Now let's look at the derivative. I just use the ddx notation of 3x squared plus 4 to the fifth. And we can use something called the general power rule, which is essentially part of the chain rule family. So you bring the 5 down, you change the exponent to 4, and then you take the derivative of the inside. So the derivative of 3x squared plus 4 would be 6x. Always have to remember the derivative of the inside. Now technically this is correct, but I went ahead and put the 6x together with the 5 and made it 30x. Of course it would be wrong algebraically. You can't distribute through the parentheses there. That's a bad algebra mistake, because this parentheses is not to the first power. Okay. Therefore, if we work this backwards, that guarantees then that the antiderivative of the result we got for the derivative right here, the antiderivative would be the original function that I differentiated, but then of course the plus c there, because there could have been at the end of this original problem, there could have been a plus number, or plus or minus a number, and it still would have the same derivative. So just kind of showing you, so yeah, that would have to be the antiderivative. But obviously that's not really the technique we're going to apply when we work these problems. Now I'm going to sort of show you how this kind of develops into the form we'll kind of be using, or you don't have to necessarily use the notation quite as formally as they are here. It'll have, a little later we'll see. Now I'm going to bring up something back from algebra called, write something as a composite function, f of g of x. That's not multiplication right here. That means you're inserting a function into another function. So f of g of x means you take whatever function g of x is and you plug it in for everywhere there's an x in f of x. So if I wanted to write that last one, I would use x to the fifth as my outer function to take care of this exponent, x to the fifth, to account for that. And then I would let g of x just be 3x squared plus 4. So f of g of x would be the same thing as f of 3x squared plus 4, which means you take this 3x squared plus 4 and you plug it right in for that x, and then it becomes 3x squared plus 4 raised to the fifth. So that's how you can write that original function that we took the derivative of in composite form. And here is the idea. See, it gets a little messy looking right here, so they kind of simplify right below. So this is, f of g of x times g prime of x dx equals big F. And remember we learned in a previous section that the big F means the antiderivative function of the little f. So then it's just f of then g of x plus c. It's not really just a straight out formula you can just plug stuff into. It's more of a negotiation process. So here they use to simplify the notation, we let u equal g of x, which gives you du equals g prime dx in the differential notation. So therefore, little fu du equals big Fu plus c. So there we go. Maybe the author's sending us a message there. So we're trying to find the big Fu there. And then of course we have to change it back into your original variable when you finish. So the idea is this technique is, I probably have this mentioned coming up, but it's known as U substitution. So what we're going to do, now we already know what this one is, but here's how I want to put this together. We're going to put this in terms of u's and du's, then we integrate, and then we change it back to our original variable, in this case, which is x, but it doesn't have to always be x. All right, so now, you know, different problems require different techniques, but these basic ones, what you're looking at here is you're looking at u being what's in the parentheses. If you have something raised to a power, whether it's, you know, positive, negative, fraction, doesn't matter, the u will be the inside. So the u will be 3x squared plus 4. Then the du would be, the derivative of this would be 6x dx. All right, now, so we're trying to piece all this together, this original integral, in terms of u's and du's. Now, I'm actually going to do this a little bit different technique in future problems, but just for this one, it works out convenient. But if du equals 6x dx, problem is we need 30x dx. So we already know we can represent this part here as just u raised to the 4th power. So we have to accommodate the stuff I have underlined here together. So you could actually rewrite this if you wanted to and put the 30x there at the end with the dx. Remember, with antiderivatives integrals, you can't bring variables outside the integral. You can never do that if it's the variable of integration, like in this case x. But you can move stuff around, you know, inside the integral. That's certainly fine. But if I needed 30x dx, I could multiply both sides by 5. Because obviously 5 times 6 would be 30. So I would have this result right here. 5 du equals 30x dx. And so that would be 5 du, and that would be u to the 4th. So then you rewrite your integral then as 5u to the 4th du, and then you use the power rule. That's simple enough. So u to the 4 plus 1 over 4 plus 1. 5s would cancel out. It would be u to the 5th plus c. Then our last step is to plug in the original representation of u in here. So it'd be 3x squared plus 4. So the final answer is 3x squared plus 4 to plus c. So, and we already know that that's correct from what we did earlier with the same example. So that's essentially the technique. Which is, when you get to this part right here, u substitution, that's also known then as the general power rule for integration. But not every substitution we're going to do is going to be a general power rule, because we'll have trig functions and things like that. But if it fits this sort of where it's raised to a power idea, you know, you can do this. And that's what I've done right here. Okay, this first notation is very complicated looking. And once again, n can't be -1. In the next chapter, we'll see what the answer is if it is -1. And then, so then if you rewrite it like I did here, so letting u be g of x, we represented this as the u, we had the 5 right here, but then the u to the 4 du, then you just do the power rule from there. So that's what's basically happening. So I kind of call it all u substitution. I don't necessarily specify and call it the general power rule, but that's, you see, I have that already named since it's right out of this particular textbook. All right, so let's kind of go with that, but I just call it all u substitution. That way it works for trig and algebraic functions. All right, so what do we have here? We have x to the 5th times 3x to the 6th minus 1 all raised to the 7th. Well, we have to let u be what's on the inside of the parentheses. 3x to the 6th minus 1. Therefore, all of this then will be represented as u to the 7th. Now, here's how I would normally do the u substitution, unlike that last example. Take the derivative. It'll be 18x to the 5th dx. But we only need x to the 5th dx. So you see I moved that x to the 5th over. So to get x to the 5th dx, we divide both sides by 18. So 1/18 du equals x to the 5th dx. So you see I wrote right up here, and then x to the 5th dx is then represented as 1/18 du. So now we have everything in terms of u. So you can't do these integration problems by, leaving some things as u and some as x. They have to all transform over, which is no problem. So then we have, of course, now the 1/18th here can come to the outside of the integral. Constants can always, multiplied constants can always move out. And then you're just left here with u to the 7th du. Simple power rule. It'd be u to the 8th over u to the 8th over 8. 18 times 8, so it's 144 u to the 8th. And then the very last step would be to replace u with what it's defined as here. 3 to the 6x, x 3 to the x to the 6th minus 1 raised to the 8th plus c. Don't want to forget our plus c. And Bucky gives seal of approval. Thank you, Bucky. All right, let's look at this next one. So what we're going to do here is we're going to need to bring, oh, you know what I forgot here? Let's see. Oh, good, that copy. Oh, where'd it go? Forgot to put the dx in the original problem. I mean, the work I did is okay, but the dx can be up there or out to the side, but I didn't have it. Shame on me. Yeah, I had it in the next step. I did not have it in the original problem. All right, so I brought the denominator up to the top. Might as well get it up. You could leave it and then move it after you've converted to u, but I decided to go ahead and move it up first. Because remember, you can't perform the power rule to something that's in the denominator. You have to bring it up. Now the 5 could stay inside, but I'll always go ahead and bring those constants out so I don't have to worry about them. Yeah, they're part of the answer, but they don't affect the process at all. So now I brought this up, made it negative 2/3, and left x dx together. So we let u equal x squared plus 3. du equals 2x dx. And we have then 1/2 du equals x dx. So that means this x dx can be replaced with 1/2 du right here. The 5 just stays on the outside. So we have u to the negative 2/3 from right here, and then 1/2 du. So the 5 can go out there and with the 1/2 to make it 5/2. Then we do the power rule. Negative 2/3 plus 1 will be 1/3. Well, dividing by 1/3 is the same as multiplying by 3 over 1. So I can combine all these constants together to make 15 over 2. We have u to the 1/3, replace u with what it's defined as, x squared plus 3 to the 1/3 plus c. And Bucky approves again. Let's see. All right, let's look at another example. So this one, once again, I pull the 7 out. I bring that radical up, so that's going to be a 1/4 power, but when you bring it up, that makes it negative 1/4 power. We have an x dx, and that means the u will be the inside part here of the parentheses, 5 minus x squared. du will be negative 2x dx. And then divide both sides by negative 2, so we have negative 1/2 du equals x dx. And so then I have the 7, which I brought to the outside. The negative 1/2 from right here can come join the 7, so that'll make negative 7/2. Now I have u to the negative 1/4 du, so I can just do a power rule. Negative 1/4 plus 1 will be 3/4. That'll put 4/3 there as that coefficient, the reciprocal of this. So we combine all that together. 4 over 2 makes 2, cancels, makes that negative 14 over 3. And then we just replace it back with what u is defined as. So it's 5 minus x squared raised to the 3/4 plus c. And let's look at this example. This one's pretty straightforward. This looks like one of our earlier ones. So you let u be x cubed plus fifth, pretty straightforward. So the derivative would be 3x squared dx, so you divide both sides by 3. 1/3 du equals x squared dx. Now, so I just put this in here, and I said this verbally a few minutes ago, but this is always a good reminder, so when Stewie's says it's important. So in other words, Stewie's saying don't ever bring that variable outside the interval. That is absolutely wrong. And one other thing I'll mention that's I'm sure I've mentioned before in one of the other integration videos is you cannot integrate the product of two functions separately. I see people make that mistake a lot, like you can't integrate the x squared by itself and you can't integrate the other one. Well, actually, you can't integrate this part to the fourth power without that x squared because you need it for the du, but I'll see people try to integrate them separately. Nope, can't do that. That's only when you have added and subtracted integrals. All right, so don't do that, and now the rest of it's easy. So the 1/3 comes out, u to the fourth, 1/5 u to the fifth. So combine them, you got 1/15 x cubed plus 5 to the fifth plus c. All right. So looks like I've included a bunch of examples here. I'm ready to go on to something a little bit different here, possibly, especially this next thing, and the ones with the trig function. That's always challenging. But so I might kind of fly through these two real quick here, but you'll have you can see the written work even if I don't do a lengthy explanation. So you let so you bring that up, make it -1/2, let u be the inside, so it's du is 4x cubed dx, 1/4 on both sides, so it's 1/4 u to the -1/2. Power rule, antiderivative, -1/2 plus 1 is 1/2, makes it 2 here. So 2 over 4 reduces to 1/2, and there you have this answer right there. Okay. Let's look at the next one, and this one you have to bring it up and make it a negative exponent. That's the only thing you have to worry about here. I brought the 6 to the outside. I can do that. The x squared has to stay. Let u be on the inside. Derivative of that's 12x squared. So I divide both sides by 12 to make that 1/12 du equals x squared dx. So this will be 1/12 du. So the 1/12 I went ahead and just brought to the outside with the 6. That makes that u to the -1/3. 6 times 1/12 is 1/2. -3 plus 1 is -2. So we have u to the -2 over -2. And then combine that together, makes that -1/4. So it's 4x cubed minus 9 to the -2 plus c, which I have no problem with negative exponents. I don't with derivatives or antiderivatives. I'm sure I've mentioned that before. However, if you're, whether this is like a quiz or if you're taking the online version of this class, the answers might be written in positive form, but all you have to do is just look for the correct answer that drops this back down to the denominator. But a student that was taking a written test in my class could leave it like this, and that would be perfectly acceptable. But it's not that hard if you're taking it multiple choice and you do it right. It's not that hard to find the correct answer. All right, this is just something, this is not an official mathematics term, a special type of integration by substitution. That's not, an official mathematical name. But I had no other way to indicate this process because it's a little bit different. Okay, now let's look at this problem. It's x times the square root of x minus 2. So we're probably thinking, which is right, you got to let u equal x minus 2, but here's the problem. Du equals just dx. See, the dx does not produce this x like all the other ones were working out perfectly, and that was the idea. That's what basic substitution problems do, is they work out perfectly. And that's why this is the first example of something even, a little more advanced than basic substitution, and then you go on to learn more advanced things, especially in Cal 2. But anyway, let's just say, for example, that would have been x squared minus 2 in the parentheses, and the radical here. Also parentheses here. So that would have been a 2 right there. Then this would have pretty much fit the same mold of all these other problems we have been doing. Because if it would have been x squared minus 2, the derivative would have been 2x dx, and we would have had our x. See? But this one does not. So here's what you have to do. You have to take, where you have u equals x minus 2, you then, to get x, you solve for x in terms of u. I hadn't had that encountered yet. So if u equals x minus 2, that means x would equal u plus 2 when you move the 2 to the other side, like so. All right. So x is u plus 2. And then u, so this will be u to the 1/2 right here. So u to the 1/2, and then you replace x with u plus 2, then du was here, du was just dx. So they stayed right here. Now you look at this step and go, well, what do I do here? Well, that's no problem because this parenthesis is to the first power. Since it's to the first power, that means you can distribute, and you're then creating two separate intervals. That's mathematically allowed, and that's the process for this problem. So I distribute. U to the 1/2 times u is u to the 3/2. U to the 1/2 times 2 is 2u to the 1/2. And so you take these two problems, and now because they're added or subtracted, either way, you can treat them as individuals. It's just when two things like this problem here, once again, I mentioned that you can't treat those as two separate integrals, separate problems and integrate them separately because it's multiplied. That would not work. But when we make this substitution, then they turn into two legitimate separate integrals that we can work out. So u to the 3/2 power rule will be 2/5 u to the 5/2 plus 2 times, this one will be u to the 3/2 and a 2/3, 2 times 2/3. So that makes that 4/3. So you have 2/5 u to the 5/2, and then plus 4/3 u to the 3/2. Then what you do is replace u back in here. So you have x minus, so it's 2/5 x minus 2 to the 5/2 plus 4/3 times x minus 2 to the 3/2 plus c. And that's a perfectly good answer. But look what happens when I put this in Maple, and look what this generates. So you might think, oh no, I'm wrong. I made a mistake here. I did not make a mistake here. Now, when you see these kind of problems and you practice them and you look at books, they'll show this kind of factored answer, which I never expect students to do, whether you're taking handwritten face-to-face class or online. If it was online, I would make sure the answers were all in this sort of format right here as this answer was. I would accommodate that. But obviously I have no control over what textbooks do or whatever. So if you were doing, like, say, a practice problem out of a book, like, say, this problem, and you go to look up the answer, and you see this, and you're going, oh no, I messed up. No, that doesn't mean you messed up. Now, for the Larson book, if you use that website calcchat.com that I mentioned in my syllabus, you'll see that it'll show, if it's an odd problem, it'll show some steps, so at least you might see enough of the steps and then not worry about if it goes from here to that last answer. But the problem is with just looking up the answer, you're only going to see this right here. So if you saw the steps, I think that would help you understand it. All right, so here's what we're going to do. Now, this, like I said, this is absolutely not necessary what I'm doing right here. Not necessary. The algebraic stuff I did here. I just wanted you to see it. See what happened. Maybe that will give you peace of mind that my answer is okay. And I didn't just mess this up. But it's just strictly algebra at that point. And all right, so I'm not going to walk through all the algebra steps here. You could ask me about it if you wanted to, but it's basically a matter of just taking out a GCF. That's a basic step, x minus 2 to the 3/2 and just took out a GCF and went from there. And then I made it look like that maple answer. Well, they have 4 plus 3x. I have 3x plus 4. Obviously, we're all smart enough to know that's the same thing. All right, so that's, and here's another example of that same technique. So you let u be what's on the parentheses of this integral, our radical, x plus 3, du's dx. So once again, we're not generating this x squared that we need. So we got to come up with that x squared, no problem. We let the x be u minus 3. From working with this, move the 3 over to the other side. X would equal u minus 3. And so we have u to the 1/2, which comes from the radical part. So now I've kind of switched places there. I'll move this to the front, and I'll move the x squared here. So x squared u minus 3 squared. Probably not likely to put a squared on a test, but I can guarantee you this, that would be the most I would make you do. That I promise. If I ever made somebody do a square, I'm not going to treat this if it was some sort of like x, x to the 10th, and you had to raise that to the 10th power with some binomial expansion. I'm going to let Maple warm up there for a minute while I'm finishing this and show you what I mean. And, well, anyway, so u minus 3 squared, once again, you have to know how to square a binomial properly. That's not u squared plus 9. You have to FOIL that out. And it's u squared minus 6u plus 9. It's 3 terms. You always have 3 terms when you square a binomial. The only way that you can multiply two binomials together and not have 3 terms is if it's the difference of 2 squares. Squares, like or x plus y times x minus y equals x squared minus y squared. But don't make that algebraic mistake. U squared minus 6u plus 9, but then we distribute it times u to the 1/2. So you just u to the 1/2 times u squared, u to the 5/2. U to the 1/2 times negative 6u is negative 6u to the 3/2. And then, of course, times 9 will just be 9u to the 1/2. So at this point, it's a little bit messy. Square is not too bad, but yeah, nothing worse than that. But it's not too bad because they're just all, and you treat them as individuals and use the power rule. So 5/2 plus 1 is 7/2, makes it 2 over 7. 2/5, 5/2 with a minus 6 there. And then 1/2 plus 1 is 3/2, makes it 2/3 here with a 9 in front. So I just kind of tidied up there 6, and then replaced it. Remember, u was x plus 3. So now you have to put x plus 3 in there. There was x. And there you can see I put this in Maple, and as I was saying, Maple gives you the factored answer. I'm saying it's not necessary to find the factored answer. So that's perfectly fine right there. Oh, I was going to use Maple to show a higher power of this, but I realized it's going to show it factored anyway, so it wouldn't accomplish what I wanted to accomplish. So I won't worry about that. All right, so let's not, but okay, that's the worst case scenario, but you would never be required to get that factored answer. All righty, substitution involving trig. Okay, this could be good. Trig is always fun. Well, you might not agree, that's fine. I find trig fun. Yep, so like I said, I'm mentioning here that u can be tricky because sometimes the u might be the trig function or the argument of the trig function. It all depends on what the rest of the interval contains. So let's see what we have here. Looks a little crowded. Let's look at that problem. The integral of x times sine of x squared. I'm having to decide whether is the u going to be the trig function itself, or is it going to be the argument of the trig function? Now remember, that's what I always joke about if you're in class. I make people use pencil in my face-to-face class so they can erase. Obviously, if you're taking it online, use scratch paper, you can use ink or whatever you want. But anyway, I always joke about that's what erasers are made for. If you make the wrong choice, you can erase this and start over. So, okay, that didn't work. Let me go back to the drawing board here. So you're not under pressure to get this right the first time. But here's the logic behind this problem. U would have to be x squared. U could not be anything involving sine. Well, how do I know that? Okay, well, fair enough. Because if u is going to be anything involving sine, and then we're trying to find du, the derivative of sine is cosine. And I do not see cosine anywhere in that interval. So that pretty much rules out sine as being u. So it's as straightforward as that as far as making your choice. So u is x squared. That means du is 2x dx. So then divide both sides by 2. So 1/2 du is x dx. Now I just drew this line linking. That doesn't mean anything mathematically, but linking the x with the dx, because that's the du part of the problem. That's what we're looking for, is the du part. So the x dx then now, those two things together form the 1/2 du. And then I came over here and pulled the 1/2 to the outside. The du still stays there, of course. And we have basically sine of u du. So all we have to do is take the antiderivative of sine, which we know to be negative cosine. Antiderivative here, not derivative. Antiderivative of sine is negative cosine. So then that just changes that from positive 1/2 to negative. And we have cosine of u, which we replace u with x squared. And then we have plus c. And that's it. All right. Now how about this next one? Cos of the square root of x and divided by square root of x. I certainly hope no one thinks that those square root of x is canceled. That would be very, very, very bad, because you have to think of the argument of that trig function is pretty much attached to that trig function. It would need some sort of identity or something to break it apart. You can't just chop it off like that. So it's cosine. Yeah, actually cos means nothing without an argument to it. So that's obviously I don't think too many people would do that, but I've seen it a few times in a handwritten situation. Alrighty, so what I'm going to do is, I lifted the radical up, get everything in a sort of all in one line there, and then change the radical. So that square root of x on bottom comes up and then just becomes x to the negative 1/2. And then then this changes this to x to the positive 1/2. And all right, so then look at this. So once again, like the last problem, there's u can't be cosine because there would have to be a sine for the derivative there, and there isn't. So it has to be the argument of the function, x to the 1/2. So the derivative of x to the 1/2 would be 1/2 x to the minus 1/2 dx. So that's good because we're looking for x to the minus 1/2. So multiply both sides. Yeah, usually we have whole numbers there and we're dividing, but this time we have a fraction. So you multiply both sides by 2 to get rid of that 1/2. So we have 2 du equals x to the negative 1/2 dx. So that radical, this part right here, x to the negative 1/2 dx, is 2 du. So that represents 2 du, and then this is cosine of u. So I brought the 2 out and left the du, cosine of u. So the antiderivative of cosine of u would be, antiderivative is positive sine. So it's 2 sine of u, replace u with x to the 1/2, or you can square root of x is fine, obviously. So 2 sine x to the 1/2 plus c. Terrific. Don't want to forget our friend the plus c. So let's see what's going on here. A tangent, a square root of tangent, and a secant squared. So this is where you really need to know your trig derivatives of all the trig functions pretty well, because that way it makes it easier for you to see the connection between the two. For example, in this problem, if you don't know that the derivative of tangent is secant squared, you're stuck. It's game over. You can't really go any further. You have to know that to solve this. So that's what dictates in this problem that we have to let u be, well, actually the square root, being under the square root makes it work this way too, but mainly the derivative of tangent is secant squared. So if u is tangent, that means the derivative of that would be secant squared dx. So that means this right here, that's a perfect fit right there for du. That is all du right there. And then the square root of tangent just becomes the square root of u, which of course is u to the 1/2. So it's u to the 1/2 du. So we have it. So we have it converted into a nice u du form. U to the 1/2 du. We can then do the power rule, so that makes that 2/3 u to the 3/2. Now, this doesn't apply if you're taking an online test. Face-to-face, I've probably mentioned before in another video, but if I haven't, that you really don't have to, we only need the plus c in the final step. I'm not sure. Yeah, I probably haven't mentioned that, but if you don't have to write the plus c. Maybe some instructors feel differently, which is fine. But the plus c just needs to be in the final answer. So tangent of x goes in for u, so I have 2/3 tan of x to the 3/2 plus c. And then Bucky approves. Now Stewie's just mentioning a little bit something here. This is more of an issue probably for handwriting exams than it is online of how you represent. But it's good for everyone to know this. Also, I shouldn't say it's just for handwritten because it's more recognition than anything else. When you write a trig function and you want the trig function to be raised to the power, there's one of two acceptable ways to write it. So if you put parentheses around the whole thing and you put 3/2, that means it's the tangent function raised to the 3/2, like right here. And that's the same thing as if you put 3/2 right there above the tangent next to the x. And then, but if you write functions like this, tan of x to the 3/2, that form implies, without parentheses, that you just mean the x is to the 3/2. That would be equivalent to as if it was written this way, as parentheses around the argument of the function, like that. So those two are kind of equivalent in ideas. So, all right, so that's good to know. Let's see what we have here. Well, now there's only one trig function here, but that's not critical because that has to, in other words, that can't be our u because there's no du for it. So this one, once again, the u has to be the argument of the trig function. But now you might look weird. You don't look at this and might go, how's 1/x going to turn into 1/x squared? Well, it does easily once you kind of rewrite these as negative exponents. So if you say sec squared and write that as x to the -1, and then you have the 1/x squared is x to the -2 dx. You then let u equal x to the -1. Du is -x to the -2 dx. All we have to do is move the negative over to the other side, which is mathematically equivalent of multiplying both sides by -1. So it leaves negative right there. X to the -2 dx. Beautiful. And so negative du then represents this. So I just brought the negative sign right out there. There it is. So then du with the negative on the outside takes care of this. and then we have sec squared, and that's u right there. So obviously this is very important that you would have to know that the antiderivative of sec squared is tangent. So the antiderivative of negative sec squared u du would be negative tan of u, and therefore would be negative tan 1 over x plus c, or x to the negative 1, same thing. Okay, there we go. Let's take a look at this one. All right, so we have sine of x divided by cosine cubed. Now this one's kind of interesting. Well, let me say first, of course, I'm bringing the cosine cubed up and making it cosine the negative 3. Now what makes this kind of interesting is that, you know, the u du, you might think, well, you know, they're both derivatives of each other in the sense that, you know, the derivative of sine is cosine, the derivative of cosine is negative sine. So how do I know which is which? So that's true, but this one, and that would really be true if it was just cosine to the first power times sine to the first power. If that was the case, you could let either one of them be u. But here you don't really have that a choice. Even though you think you might have a choice, you do not. In this situation, you have to let u be the cosine, the one that has the exponent. The one that does not have the, well, it has an exponent of 1, but I mean, you know, a non-1 exponent. That has to be your du, because du can never be raised to a power. There would be no problem where you had like, well, part of your integral looks like this. Du squared, you know, that's nonsense. That doesn't mean anything. So that's what dictates in this case is whichever one is the one that's not to the first power has to be u. Now you might be thinking, what if they're both not to the first power? Okay, welcome to Cal 2. That's where that kind of problem will be discussed, but not in this class. So yeah, that's what I'm saying. You know, integration. You kind of, as you progress through the class in Cal 2, you just learn more and more types of things, more and more types of functions to integrate. So that's how. So we let u be cosine, because obviously we'll take care of the negative 3, because we'll raise u to the negative 3. Remember, you don't leave the exponent with the u. I might not have made that totally clear earlier, but let me say it now. That's not just for trig. That's for any of the problems. I might have forgotten to say that, but that's okay, because I'll say it now. Is you don't let u have, I mean, there might be a rare exception, but we don't want u to be the function raised to the power, because we'll just raise u to the power after we've done it. So you've seen me do that every time, even though I didn't maybe say it before. But that's the way I've done every problem, so we don't have to like go back and correct everything I've done, because I did it right. So, but I want to at least say that. So u is cosine, so you see that makes that then u to the negative 3. So don't leave the exponent with the variable, or in this case trig, or any of these other problems. I'll just scroll back up there just for a second. Let's scroll back up here to one of the algebraic ones. Not the special, any of these. See, like these two real quick. So you see u didn't contain the exponent, but then we raised u to that power. U didn't contain the exponent, but we raised u to that power. So that's what I'm talking about. So the u did not have the overall exponent. Beautiful. And then now, so the derivative of cosine would be negative sine. So it's real easy to move that negative over and make it negative du equals sine of x dx. So this will be negative du right here. So I'll toss the negative to the outside. We raise u to the negative 3, then du takes care of that sine x dx. So that's all gone. Do the power rule, you have negative, which is negative was already there, of course. U to the negative 2 over negative 2. The negatives cancel. Leaves 1/2. And then, so it's 1/2, and then see how I wrote it, cosine of x and next to the negative 2, that's correct. Now it's possible this kind of answer might do this to you just because of the relationship of the reciprocal trig functions. I mean, yes, that's the same as 1 over cosine squared, but that just happens to be the same thing as in a secant squared, because secant is 1 over cosine. So I'm not saying it has to be ever written this way, but it could be where you need to recognize that answer, at least when you see it as a choice. But a handwritten problem, I would be perfectly fine with it, leaving it just like this. Now here's a different approach where if you, I mean, I like the first way better. And I just basically split this up as sine over cosine. That left 1 over cosine squared. So you see, you multiply this part together right here, you're going to get the original problem. That's obviously very important. I can't just make up something that doesn't match the original. So that's going to be tan x times sec squared. So in this case, you would let u be tan and du would be sec squared, so it fits real nice. So it's u du, which is 1/2 u squared plus c. Now, which is then 1/2 tan squared of x plus c. Now notice that these are written a little bit different, but like I said, based on that other Stewie says thing I showed you, those are equivalent. So in other words, I could have put the 2 right there and made that secant squared, or I could have put parentheses. But that's representing the same thing in the sense that the trig function is raised to the power. So that's both correct notations. Now you look at this and go, hey, wait a minute there, fella. They're 2 different answers. Well, yes, and that can happen with trig intervals. You can because how the trig functions kind of relate to each other with identities, especially the Pythagorean identities, which are like sine squared plus cosine squared equals 1, and 1 plus tan squared equals sec squared. Now, what makes an antiderivative technically, whether it's correct or not, so you might know which of those is correct. They're both correct. Because the rule for being a correct antiderivative is, does the derivative of your answer equal your original function? So if your derivative of your answer equals your original function, then it's correct, even if they're 2 different looking answers and they match. Then they're both right. So all I did here was I took the derivative of, okay, I didn't actually finish this though, did I? But anyway, the first answer, the sec squared, so I wrote it like this, the derivative, and then I put tan squared of sec squared minus 1. But anyway, let me just mention this one thing real quick without finishing this. If I distributed this through the parentheses, I would have 1/2 sec squared minus 1/2. Well, when you take the derivative of the minus 1/2, it's going to go to 0, just like the derivative of c will go to 0. So both sides are basically the same thing as saying taking the derivative of sec squared. Therefore, they are equivalent. Because that derivative, like I said, of the negative 1/2 would just go to 0. So it is possible to have different looking trig answers and still both be correct. Because of how the functions relate to each other. Alrighty, let's see what we got here. Alright, this one we're going to have to, because there's no other trig functions, so you'll have to let u be what's in the parentheses. X over 2, so you get the derivative of x over 2, which that's just 1/2 x. It's funny, sometimes I'll see people take problems like x over 2 and do the quotient rule. They don't realize it's just 1/2 x. So let's don't make things, any more complicated than necessary. So it's just 1/2 x. So the derivative then would be 1/2 dx. So you divide both sides by 1/2, makes it 2. So it's 2 du equals dx. So therefore, 2 du is dx, so it goes right there. And then you have, that becomes cosecant squared of u. So this is where you got to know that the antiderivative of cosecant squared is negative cotangent. So I just kind of wrote it this way, but actually then if you work it backwards, then the antiderivative of just cosecant squared would move the negative up there and make it negative cotangent. So you kind of, once you get that step, you pretty much have to know that, or you can't go any further. There's no magical way to work it out. Let's see. So you have negative 2 cotangent u, and then replace u with x over 2, and don't forget your plus c. Now this one, tan squared. For this one, you have to use a trig identity to do this one. You have to replace tan squared with sec squared minus 1. The reason for that is tan squared doesn't have a natural antiderivative, but sec squared does. Sec squared already has an antiderivative that's tangent. And then the antiderivative of -1 would be negative x. And then, of course, your plus c. Probably seems odd to have an x as an answer with the trig function. All right, so now this one's a little bit, we did one with a power of sine and cosine, but that 4x is going to make a slight difference, an important difference, especially if you're trying to get the right answer. It's going to be very important that we realize we're going to have a chain rule issue here in our derivative, a minor chain rule issue, but an important one. So once again, we use the same argument that I used a little while ago, that if you have sine and cosine multiplied together, whichever one of the two has the exponent that's not 1, that has to be the u. So in this case, it's sine cubed, so therefore u would have to be sine. And then we'll raise it to the third power. We'll say, that'll be u cubed. Once you identify what u is here, that'll be u cubed. Now, very important, we've got to remember our chain rule. The derivative of sine 4x is not cosine of 4x. That's close, but it's 4 cosine of 4x. Because of the chain rule. Obviously, that's very important. So therefore, it's 4 cos 4x, so then we divide both sides by 4, and we have 1/4 du equals cos 4x dx. So it generates that extra 1/4. So that 1/4 is the first 1/4 right here. And then just by coincidence, because this is u cubed, when you take the antiderivative of u cubed, you're going to have 1/4 u to the 4th. So you just have two independent 1/4 that happen to be the same thing. Multiply those together. And then you get 1/16 u to the 4th. And now you replace your u to the 4th with sine of 4x to the 4th. So you have 1/16 sine of 4x all to the 4th plus c. All right, come down here. Let's look at this one. The integral of sec squared x dx over 3 plus tan x to the 5th. So I brought that denominator up, which I could have waited, but I always like to do it first. And of course, now I say that, I may have another example where I didn't do it first. Even though whether it's on the bottom or the top, the u is still going to be 3 plus tan x. But at some point, you can substitute first and then raise it up, whatever, and then make it. But I just did it like this. So that makes it u, so the du then will be sec squared x dx, which actually fits perfectly. No dividing or combining numbers or having to adjust or anything like that. Let's see. Okay. And then we just end up with something as straightforward as u to the -5 du. And antiderivative would be -1/4 u to the -4th. So then we replace our u, and we have -1/4, 3 plus tan x to the -4 plus c. So how about this next one? Let's see what we have here. All right, so we're going to let u be x to the 4th. And then the u will be x to the 4th, and du then is 4x cubed dx. So 1/4 du equals x cubed dx. And we got 1/4 sec squared u du. And that's just straight up 1/4 tangent of u. So so that's where knowing antiderivative of sec squared would be tangent. And then we have 1/4 tan of x to the 4th plus c. Okay, so I don't think that one was too bad once you kind of get the hang of this. Now, substitution with definite integrals. Now this is two ways you can kind of do these problems. I prefer what I have here written in this statement. That's why I'm just going to go ahead and do these problems. I think it's easier, and you'll see why I think it's easier here in a minute. So let's take a look at this example. Integral from 0 to 1, x times the square root of 1 minus x squared. All right, pretty straightforward substitution. Just obviously this is a definite integral this time instead of indefinite. We let u equal 1 minus x squared. Therefore, du would be negative 2x dx. And then negative 1/2 du equals x dx. Now here's what I was talking about a couple of minutes ago, is that, yeah, you can integrate this in u and then change your answer back to x and put in 0 and 1. But that's very inefficient when you can just do this. Is it basically you're changing the limits of integration from x to u. Now, because sometimes it's better if you do it this way, because sometimes I see people will integrate in terms of u and then forget to go back to x, then they'll put the upper and lower limits in there while it's still u, then that will be variable u, and that would be wrong. All right, so now I'm going to put the upper limit 1 in here. 1 minus 1 squared will be 0. Put in 0. 1 minus 0 squared is 1. And that's just an absolute coincidence there that 1, 0 went to 0, 1. That's not a automatic occurrence. But anyway, so we got a negative 1/2. So the du will be x dx. So the negative 1/2 is here when you divide both sides by negative 2. That comes to the outside. You now have 0 on top and 1 on bottom. And then you have u to the 1/2 du. Now you might think this is weird because, most definite integrals are always, I'll say most, all of them usually are, I think, but there might be an exception. But the lower number is supposed to be on bottom and the larger number is on top on your limits of integration. Well, when you, and it is in the original problem here, but when you change the limits of integration with your substitution variable, all bets are off. Anything can happen. So that's why it's okay that if you end up with a smaller number on top and larger on bottom. Now you could work this out as is, no problem, no problem. But this is just something I like to do. This next step is not mandatory. I like to use that property of definite integrals that says if you multiply by negative, basically you reverse the limits of integration. So what I'm effectively doing is I just want to get rid of that negative. I just like to not have fewer negatives, least chance of making a mistake. So multiplying by negative makes that positive 1/2, and it just flips around the 0 and the 1. So, but you can get away without doing that, no problem. So easy power rule, u to the 1/2 is 1/2. Well, 1/2, I'm sorry, this 1/2, but it makes it 2/3 u to the 3/2. But keep in mind, this 1 and 0 now is not the original 1 and 0. It's limits of u. That means I don't have to go back to x. I don't have to change this back to x like we do for indefinite integrals. Plug in the 1, get 1. Plug in 0, you get 0. So the answer is 1/3. Maple's showing us it's also 1/3. Now here's one that I have as set up, do not evaluate. I don't know why I did that, but that's okay. I could have easily just finished the problem. It wouldn't have been that difficult. It's going to be a very large number, though, because you're going to have 7 to the 5th power involved there. But all right. Well, that's good practice, though. Obviously, once you get the setups, the skill, once you shouldn't be too hard to integrate it once you get it converted to u. All right, let's look at this. So we got u equals x cubed minus 1, which makes du equals 3x squared dx. Divide both sides by 3, so your 1/3 du then represents your x squared dx right there. Change the limits of integration, and we never have to go back to x again. Plug in 2. 2 cubed minus 1 is 7. Plug in 1, we get 0. So you see that I wrote everything down here. That's 1/3 du. That's u to the 4th right there. So like I said, I didn't quite finish it. It would have been easy to finish. But so 1/3. Now we're going from 0 to 7. U to the 4th. So I would have done 1/5 u to the 5th. And then would have put it in 7 and 0. So it would have been basically 1/15 times 7 to the 5th, whatever that is. So pretty good size number there. That would have been the answer, because 0 would have been 0 at the low end. All right, let's look at the next one, a substitution problem. So u would be 4 plus x, because that'll make that u to the 1/3 right here. Du is just dx, so there's a perfect fit. We don't have to divide by anything. Fits perfectly. Plug in 4. 4 plus 4 is usually 8. 4 plus -3 is 1. So now we're going from 1 to 8 of u to the 1/3 du, so it makes it 3/4 u to the 4/3, 8 and 1. And so you have 8 to the 4/3 minus 1 to the 4/3, and since 8 and 1 both have cube roots, that's why this is working out to not have a radical answer. All right. So, and you work this out with a calculator, whatever you want. You see I did right there in the third box there. Just work it out in the calculator. There it is, using whether it's an old school TI-83, you have to use the F in it, put that variable, then the X, and then lower and upper limits. The newer 84 operating systems, the one, not in the beginning 84s, you still had to do it this way, TI-84s, but now the newer ones, 84, the Inspire CX, you're not supposed to use the Inspire CAS, on my test at least. And then what's the new one, CE, I think, or something or another. But yeah, you can put it more in a integral looking format. But anyway, you see I'm coming up with 45 over 4 all over the place, just like Maple did. So, okay, let's see what we got here. How about this one? So we got a couple more here. So, okay, gonna let u be the 1 plus 2x squared. Du will be 4x dx. 1/4 du equals x dx. Put in 2. 1 plus 2 times 2 squared will be 9. 1 plus 2 times 0 squared will be 1. So our new limits of integration are going to go from 1 to 9. They were 0 to 2, now they're 1 to 9. Now you have to deal with the 1/4, of course, here. So you got a 1/4, 1 to 9, and then, of course, you got to bring that radical up, which makes it a negative exponent. So it's u to the negative 1/2. Use the power rule. So it's negative 1/2 plus 1 over 1/2. So it makes it 2u to the 1/2. And that reduces to 1/2. And then we have 1/2 times 9 to the 1/2 minus 1 to the 1/2. Well, 9 to the 1/2 is just the square root of 9. So it's 3. 1 to the anything is 1. So you basically have 1/2 times 2. And so you end up with 1. And you see Maple gets 1 here. And this will be the last problem. Got a trig one here. Here we go. You know, we've seen a couple of problems like this before. The u has to be the sign because it's the one raised to a power other than 1. That makes du 3 cos of 3x dx. Don't forget the chain rule, very important, obviously. So you have to divide both sides by 3, which makes it a 1/3. That's terrific. And change the limits of integration. Put in pi over 6, sine of 3 pi over 6, which is the same as sine of pi over 2, makes that 1. And then you put in 0, sine of 0 is 0. And then we have, so it works out, it looks pretty complicated, but it works out kind of nice. So there's the 1/3 I brought out to the outside. So all I'm left with here on the inside is just u to the 5th du. I've changed the limits of integration, meaning I don't have to go back to x again. I don't have to plug in anything back into x. So we just have this integral right here, which is pretty easy. So it's 1/3 times 1/6 u to the 6th would be the antiderivative of u to the 5th. Put in 1, put in 0. We have 1 over 18, basically times 1 minus 0. So we have 1 over 18, and Maple says it's 1 over 18. Okay, that concludes this video for integration by substitution.